I spent a lot of years building software on a wide variety of different platforms. And now I'm getting a little bit into mobile apps, but not deep enough that I actually know what I'm doing yet. And finally, I'm a big fan of Ozcode and all the work that is being done by this company. So today we're going to go through a few things. I'm going to take you through some famous bugs that we have seen over the years. I'm going to talk about some different exciting kinds of bugs, how to defend against bugs, and then how we can use Ozcode to help fixing production bugs. All right. So to start off, unfortunately, software bugs are pretty much everywhere. Everybody here has, I'm sure, encountered a bug in production code, whether it's in your own software or in some piece of software that you use. Mistakes are just a fact of life when it comes to software bugs, but some of them are minor things, whereas some of them are much more complicated and difficult to diagnose problems. Some of them have wide-ranging effects. So I have a few fun, notorious bugs that I wanted to chat about. So the first one that comes to mind, and is I'm sure in people's minds if they happen to be in the southern United States, specifically Texas at the moment, is Blackout. So back in 2003, there was a huge blackout. You can see kind of a picture of it on the slide here, where a vast quantity of the northeastern United States and spreading all the way up into Canada, Toronto area, lost power for as long as 2 days. So this impacted 55 million people spread across 2 countries. And when they were doing the analysis of what had gone wrong here, it turned out that one of the contributing factors was that a piece of software that was supposed to help run the energy management system called XA21 had a race condition in it. And as a result of this, it actually resulted in the screens in the control rooms not being updated. So the power station controllers weren't aware that there were power outages and weren't able to react properly to it. So this caused kind of a cascade effect and resulted in power being lost to all these millions of people. So this was a big problem because it knocked out telecommunications, water supply because pumps couldn't run anymore, transportation, all over the place, lots of big problems. I remember at the time being somewhat amused because there were stories coming out of New York City of people going down to use the subway or waiting for hours for the elevator to come and collect them and not realizing that all of those systems run on electricity. So instead, people had to walk downstairs and then hike home through the streets. So that was an interesting story. Another good one was the story of the USS Yorktown. So this is a picture of this ship, and it was being used as a test bed for new technologies in the US Navy. So they had a lot of computers on this system, on the ship, and they were using it to run the various systems on the ship up until somebody accidentally entered a 0 into a field. And this resulted in a divide by 0 error, which knocked out propulsion, weapons, radar, everything on the entire ship for at least 3 hours. There are kind of competing stories about whether the ship was able to be rebooted or whether it had to be towed back into port, but it's still a really good lesson. I think the key takeaway here was don't run your warships on Windows NT 4. This is another one of my favorites. So this was in World of Warcraft. So for people who are not familiar with this, it's a massive multiplayer online game. And in this game, there was a new quest unlocked for people to go and play through. But it was a fairly advanced quest, so you needed to be a high-level player to compete in this. In the quest, people would be infected with this kind of plague, and the plague could jump from party member to party member within your group, dealing some damage to you. Now, this was supposed to be confined to the area in which the quest was taking place, but people were able to leave the area while being infected with this plague, and it was spread to players of all levels. So if you were a low-level player that had just started to play the game and you were infected with this plague, it did enough damage to kill you instantly. But this was actually a pretty fortuitous bug because it was used by researchers to examine how infections spread throughout populations. So this was one of, I think, 2 very similar incidents that happened in the world of Warcraft, which were used by researchers later on to model diseases. And then the final one that I want to talk about, and this is one of my favorite ones here, is the game Civilization. So this was Civilization 1, released back in probably the early 90s. And in this game, you play as a world leader and you try and take over the world. So one of the computer-driven players that you would compete against would be Gandhi. Now, Gandhi is known for being a fairly pacifist leader. So when the designers were building the game, they gave him a low aggressiveness rating. So this aggressiveness rating was like 1 to 8. So I think they gave him an aggressiveness rating of 1. So he was the most pacifist of all the world leaders. However, there were some conditions in which people's aggressiveness or world leaders' aggressiveness would be decreased. In fact, in some cases, decreased by 2. Now, they had used an integer to define this, and unfortunately, when they decreased Gandhi's aggressiveness by 2, instead of going back down to 0, it ended up at 255 because the integer wrapped around. So he became ultra aggressive and became known as Nuclear Gandhi. And this was a bug that was kind of so popular that it worked its way through the rest of the Civilization game. So instead of being pacifist, he was super aggressive and had a tendency to launch nukes against anybody who disagreed with him. So some of the bugs that we uncover end up being pretty common. So there's one thing that we're good at doing as computer programmers, it's naming things. So we've come up over the years with a bunch of different names for the kind of patterns that we see of bugs in software. So just as you might have patterns for design patterns or names for design patterns, we have names for some common software bugs. So I thought I'd go through some of the kind of fun ones that we've seen over the years and talk about what those look like. So one of my favorites is a Heisenbug. So this is named after physicist Werner Heisenbug, who coined the term the uncertainty principle. You might remember this as if you know the position of a particle, you can't know the velocity of the particle and vice versa. This isn't exactly the right interpretation of his theories, but it's close enough for us. So a Heisenbug is one where when you observe the behavior of the bug, the behavior changes. So there's lots of examples of this out there in programming. For instance, if you're compiling a piece of software in debug mode, it's going to change the optimizations that the compiler makes. So the result of that is that the code that you come out with when you run in debug and when you run in release mode might be subtly different. So it might just be that there are some timing changes because there are debug statements that are removed. It might be that optimization paths or unrolling loops a little bit differently. So this makes it very difficult to debug this sort of problem because as soon as you build in debug mode and attach a debugger to step through the process, things act differently and you might not be able to have that bug exhibit itself anymore. This can be very tricky to solve. Another one is the Schroding bug. So this is a bug that goes unnoticed until you observe it and go, how did this ever work in the first place? I'm sure you've run into those issues over the years. Oftentimes, I found this to be the result of a competing bug. So if you think back to school, when you were doing your math homework, did you ever run into that situation where you completely messed up the work that you needed to do to solve the math problem, but you still ended up with the right answer? So I found this happened to me a lot in kind of calculus classes where the tendency was that the answer was either 1, 0, negative infinity, or positive infinity. So it was like a 1 in 4 chance of guessing the right answer, even if you had all the work wrong. So for this one, you might imagine that you have an off by 1 error in a loop, which is a very common problem. But at the same time, maybe that one element in the array is null. So instead of, as soon as you fix that off by 1 error, then you start running into the null problem. And this bug just kind of appears from nowhere. So this is an example of what it might look like in the code here. We can see here that this iterator, which runs from one up to the number of licenses, should probably be running from 0 to the number of licenses. So in this case, we would have that array bug, but it might be hiding a different bug, which is that the first license in the array is always null. So if we can manage to fix the first bug, we're just going to be hit by the second bug. The third one that I want to talk about was this Mandelbug. So these are devilishly complicated sorts of bugs that are so complicated and span so many levels of your application that you kind of start to wonder if it was intentionally created. Most people can hold about 7 pieces of information in their mind at any one time. So as soon as you start to get to a bug that has more concepts in it than that magic number of 7, it becomes way more difficult to solve the problem. So if you have a piece of software that has a large number of degrees of abstraction, and you discover a bug in the top layer, but it's really something in the bottom layer, then you have to be able to keep in mind how the code works and how data flows through 5, 6, 7 layers. So these sorts of bugs are very difficult to solve because you just can't keep enough information in your brain at any one time to understand what the bug might be. All right, so this is the bit where I get to be a little bit controversial and say unpopular things about programming. So these are some of the things that I think help defend against bugs. And these are things that I've just discovered in my 100 million years being a computer programmer. I am shockingly old. So the first thing is single-threaded programming. I think that that really helps avoid a lot of bugs, a lot of situations where you run into race conditions, where you're editing variables from 2 different threads at the same time. The behavior becomes very complicated in those situations. As soon as you start getting into stuff like, well, I'll put a semaphore here so that nothing gets into this critical section. And then, well, what happens if we crash in a critical section? Then we need to remember to unlock that semaphore. Those sorts of things are very complicated and difficult to manage, especially because now we're getting into a world where you might have 8 or 16 or 64 processors on a single machine. That's not uncommon at all. A lot of cell phones now come with 8 or 16 cores on them. So you're going to have a lot of different threads working at the same time, which often exercises these multi-threaded bugs. So there are ways around this. If you look at a programming language like JavaScript, it's inherently single-threaded by nature. You can do multiple things at the same time, but the way that that's done is that you kick off a process and then you have it report back to you when it's done. So everything still ends up in that kind of single thread. And then in other programming languages like C#, there are tasks, and Java has tasks as well. So using these higher level concepts really helps defend against a lot of these difficult to diagnose threading bugs, but at the cost of a little bit of overhead on top of it. I think strongly typed programming languages are a great defense against a whole class of bugs. So JavaScript is my usual victim that I think about in these cases. So in JavaScript, you can assign a variable as an integer and then change it as a string and then as a Boolean. So you never really know what type of variable is. And as a result, if you're deserializing JSON or something like that, then you often run into these situations where data types are not what you expect them to be. And JavaScript just gets really weird with things in that case. So things like empty strings being equivalent to false, and the whole concept of falsy things. So this is something that I would encourage people to avoid. If you are writing JavaScript, there are tools available to add a layer of strong typing on top of JavaScript. So something like TypeScript, I think, is a really good tool to avoid a lot of bugs. Functional programming languages are another excellent tool to avoid bugs. And this is probably the super controversial topic here, that I think that if you write in a language like F# or Scala, you're going to end up with far fewer bugs than you would if you wrote in a language like C# or Java. And that's because functional programming languages introduce a lot of powerful concepts, especially around immutability. which means that once you've assigned a variable, then it keeps that value from that point forward. And you have to be really explicit about changing the type of that, or to change the value within that field. So this ends up being really useful. It avoids race conditions, it makes efficient use of memory, all that sort of stuff. So functional programming languages, especially ones with strong typing, definitely an interesting avenue to investigate if you're looking to avoid bugs. Unit support inside of languages is another fantastic thing. If you're doing any sort of mathematics or science calculations, then having units attached to your numbers inside of a programming language is a fantastic way to avoid bugs. You might remember a few years ago, NASA unfortunately crashed a rover into Mars because of I think they missed Mars completely because of a unit conversion problem between miles and kilometers. So if they'd been using a language like F# that had support for units in it, then they would never run into that problem, because the compiler would have said, oh, you're trying to add two incompatible types. You can't add miles and kilometers together without doing a conversion from either miles into kilometers or to kilometers into miles. And this sort of unit concept can become very complicated and very powerful, so that you can derive units so that you could have things like kilometers a second and be able to convert that into miles a minute and know that those types are compatible or incompatible. So units are a fantastic tool for that. And then nullable reference types, which were introduced in C#8, make null explicit inside of your application. So having null as a potential value has been called the billion-dollar mistake by actually the inventor of null. So this is a thing that you can avoid by being very explicit about what things can be null in your system, and then putting guards against them being null in every place that they're used. So like I say, in C#8, this is called nullable reference types. And then in a lot of functional programming languages, you would avoid nulls by using an option or a maybe monad, which is another powerful way of avoiding bugs in software. So the end result of this is that no matter how hard you try, you likely don't have bug-free code. So what are some of the defenses that you can put in place to avoid your entire system crashing and you being kept up till 3 in the morning trying to debug problems? So the first thing that I always push people towards is to add logging to their code. Logging is a super powerful tool so that you can see into your system and see what the state of it is and what the state of it was when there was a bug found. I like to use centralized logging in some sort of a searchable system. So something like Application Insights is good for this. There's a ton of other products out there, Datadog, Sumo, Logic, lots of stuff out there that allows you to do this. So this is especially important if you have any sort of a distributed system. So if you're doing microservices where a bunch of different processes are involved in every message that you send through the system, then being able to log everything together is wonderful, and being able to correlate events one with the other will really help you out. And then finally, you want to set up the ability to have alerts from this system. So if you have any reasonable system out there, it's going to be producing a lot of log data on a daily basis. Too much log data for you to read through by hand. So the best thing to do is to set up alerts that look for specific patterns inside of the system and then warn you when those happen. So I've seen a lot of this stuff done and done in a very interesting way, coupled with artificial intelligence now. So what you can do is you can pass all of your data into this system, and you can build yourself a baseline and then have an artificial intelligence system that looks for things that aren't typical inside your system. So they might spot things like, hey, we've seen an elevated error rate from this one particular component today. That's something that needs human investigation. Typically, we see 5,000 requests a day to this other component. Today, we've seen 50,000 requests. This is well beyond what we would expect to see as part of normal operations. So we're going to flag this and have a human being come and investigate it. So even if you have logging in your own code, that doesn't necessarily catch everything that you need. logging is fabulous for this, but if you're relying on any other sort of system, then it's likely that they might have problems in them too. So infrastructure itself can fail. If you are running on a cloud, then you're probably using some sort of cloud-hosted database. This could be failing. You might be using an app service that could fail in some sort of unexpected way. Databases, firewalls, external services, all things that can fail and affect your system's overall health. And you need to be able to get some insight into how that is working for you. So if you happen to be deployed on Azure, there is an amazing suite of tools out there, which falls under the moniker of Azure Monitor. And it brings together a whole bunch of different tools in a suite that should allow you to react and respond to problems inside of your system and spot those problems in the first place. So they have divided theirs up into about 5 different broad categories here. So the top one being application insights, container insights, VM insights, and solution monitoring. So these allow you to see problems inside of your application. There's ways to visualize this in dashboards or views or even out into Power BI. So this allows you to create Swish presentations or create dashboards that people can see all the time so that they can humanly spot problems. You might want to analyze these problems. So this is where it comes down to those places like, hey, we have a problem in this system. It's not performing the way we normally expect it to work. So we would catch that at the analysis step. And then we might want to respond to that. So that could be as simple as just sending people out alerts, or it could be that you might need to auto scale a particular system. So you're seeing more than your typical number of requests come in. The first defense against that is probably just to scale the system up so that all those requests can be handled. And then finally, there might be a need to integrate this with other places inside of your tool chain. So you can hook problems up into application or into logic apps so that you could send an email to somebody to tell them there's a problem, take compensating action. You could even do such impressive things as, we're seeing higher than average load on the website. We're having trouble keeping it up. Trigger this change, which pulls down the number of ads that we're showing online so that people aren't seeing our ads, clicking through and finding that there's a problem and overloading our servers even more. So these are all interesting things that you can do if you're inside of Azure. If you're deployed to AWS, I don't think that the solutions there are anywhere near as mature as what is on Azure. There is certainly stuff there, but you're going to end up building a lot of your own tooling out on AWS. So they have a tool called CloudWatch, which is probably the closest thing to application insights. But the search facilities there are not as good in my mind. The visualizations are certainly not as mature as something like Power BI or even the dashboards in Azure. So you're probably, if you're going to be running on AWS, you're probably going to end up deploying something on top of it like Elk Stack and being able to produce pretty graphs in Kibana or Graphena or something like that on top of what is already in AWS. So I have found the experience on AWS to be frustrating when I know what exists on Azure in the same space. So I think this is one of those few spaces where Azure is miles ahead of AWS in their facilities. So we are going to take a little look today at application insights as our primary entry point. So that exists here in this insights tier. And what it looks like is basically this. So this is a very simple default dashboard that I might have on one of my sites here. And we can see that it's logging the number of failed requests that we have to the system. It's logging the server response times. For this particular site, we have some background tasks that also report themselves as requests. So don't be scared that it's taking us 15 seconds to respond to user input. It's not actually. We just have some background tasks that report that out too. But I'm sure that having looked at that, you have immediate insight into the performance of this system. We can see the number of server requests that are going through. We can see the availability. So these are just like the out-of-the-box graphs that you get, and you can add all sorts of additional graphs on top of this, and you can do log searches and come up with some really interesting insights. I've seen some great reports that have come out of the Azure DevOps group themselves, because of course they run on Azure and they use application insights, and they have got some really interesting graphs and reports and tools set up. So for instance, they have a bunch of machines out there that are running Azure DevOps, and if they notice higher than average error rates on a particular machine, they will automatically pull that machine out of rotation and destroy it and replace it with a new machine. And all of this just happens in an automated fashion behind the scenes. If you are running any sort of a distributed application, then this tool, again, kind of free out of the box in Application Insights, is the application map. And this allows you to see where information is flowing inside of your application. So for this example here, we can see that there's a front end and that it makes a lot of calls out to this authentication service along the top here. Now, unfortunately, 19.5% of the calls of this service are failing. Now, that might be okay because this is an authentication service, and I would expect calls where people had entered the wrong passwords to show up in that too. But in other places, we can see that there's a great number of failed requests. So right along the bottom here, we can see as much as 50% of requests are failing out to this particular service, plus its response time is almost a full second. So this gives you a really easy way to see all the dependencies inside of your application and spot those which are taking longer than they should or producing more errors than they should. And this stuff, if you happen to be using .NET for your application, is all instrumented for you automatically. So you'll be able to see HTTP calls in here, calls out to Azure services, calls out to databases, all those sorts of things just get displayed inside of this screen for you. Basically, all you need to do is just install Application Insights. So I'm a big fan of this screen, and as a consultant, when I go into people's companies and I install Application Insights for them, giving them this screen right off the bat makes people super impressed and super happy with what we've done, because this gives them a level of insight into their application they've never had before. And we frequently find problems with services right away just by looking at this particular page. However, there are some limits to logging. One of the big problems is you need to know what to log, and you might not know what it is that you need to log because you don't know what's going to throw exceptions. So inevitably, by Murphy's Law, what you need to log is not what you've actually logged. Every time that you run into a bug, you add just a little bit more logging into the system. But it's just kind of like playing a game of whack-a-mole that you never quite get the logs in the right place. So you end up logging a bunch of stuff. And the more mature your system becomes, the more logging you tend to add. So it's not unusual for systems that I have worked on that have maybe 10,000 users to produce 70 or 80 gigabytes of logs a day. And there is a cost to that logging. So I have certainly spent, I don't know, $400, $500 a month just on logging. And even then, I run into situations where I go, I've not logged that one critical piece of information that would have let me solve this bug quickly. If I need to make a change to that logging, then I have to make that change in my development environment and run it through the normal build pipelines and get it out to production. If you're fortunate enough to be dealing with a system where deploys are commonplace and you do 2 or 3 of them a day, then that's not a big deal because you can push that into the build pipeline and go for lunch, and by the time you come back, it's all deployed into production. But I think there are vanishingly few companies that actually work in that fashion. We certainly hear about it with like the Netflix and the Facebooks and the Flickrs of the world. But for kind of everyday companies, it's less common to have that sort of speed of deployment. So if you need to put a change in for logging, it might be a week, it might be 2 weeks, stuff might have to go through a change management board, and all that time, you've got this bug out in production that you're unable to reproduce or understand. So that damages your reputation and it damages your ability to serve your customers. So let me give you an example of a problem that I had to solve recently. And this is for a company that deals with parking lots. So this particular company owns a bunch of parking lots and has machines at every parking lot where people go and put in their credit card or put in some cash to be able to park there for a certain period of time. So typically you go and put in a license plate number or a stall number and say, like, I'm going to park here for 6 hours and we'll charge you $20 for that. So we had an issue that system that reported to us what people had paid and when they had paid made a subtle API change. And the data that was being reported back to us was a little bit different in shape from what we were typically expecting it to be. Now, it was throwing a warning, but it wasn't throwing an error. So we weren't actually seeing this problem show up in any of our reporting tools because we were just looking for errors instead of warnings. So for a couple of days, we didn't receive any information from this particular parking lot because of this API change, and we didn't notice it until we had done the cardinal sin of giving somebody a parking ticket that didn't deserve it. This is a big problem because nobody likes getting parking tickets, and it gives them a bad taste in their mouth that they've got to call somebody up and argue about a parking ticket. And even once we had figured out that we were not getting that data back, it was very difficult for us to debug this problem because the way that this particular API worked involved very complicated signatures, HMAC signatures. So we couldn't really just throw a Postman request at it to try and figure out what the problem was. So we ended up just like deploying out changes in the hopes that it would fix the problem. We did get lucky and managed to fix the problem in a couple of hours, but it was a tense time. So it would have been nice to have some way to solve that problem in a better fashion. So what we really wanted to be able to do was debug against production, but this was a live system. We couldn't really like pull it down to attach a debugger to it. The debugging environment doesn't always work very well when you try and attach to it. And we didn't want to run the risk of attaching a debugger to the environment and then breaking other processes that we're trying to call similar code paths because we had a breakpoint in there. So sometimes what you really want is to be able to get in there into production and debug it. You might have test environments that closely replicate production, but there's always going to be some small, subtle difference that you don't understand or you don't have time to investigate. It might just be that the load on production is shaped a little bit differently from what you're trying to simulate and test. It might be that databases are configured slightly differently. In our case here, we had a UAT environment, but deploying to that environment is kind of a pain. And we actually have a weird difference between UAT and production in that UAT is about half as performant as production, even though it's on exactly the same hardware and it's been terraformed up inside of Azure to be exactly the same. Performance is just like really different between the two environments. We never really worried about it because the production environment is the more performant one. So if it had been that production was less performant, we probably would have investigated. But in this one, we're prepared to take a little bit of pain. So if we had had something like the Ozcode production debugger available to us, then I think it would have made it a little bit easier for us to solve our problem. So let's take a break here and go and take a look at a piece of software that we've written for demo purposes here and see if we can solve a problem in it. So I'm going to switch over here. What the point of Focus Assist is, if it's going to tell you that it's hiding notifications using a notification. Anyway, so this is Eshop On Web. So this is a fairly simple little shop for buying .NET branded stuff. And we are going to buy a few things today. I think maybe we'll buy a couple of these coffee mugs. So we'll buy 3 of those and just put those in our cart. And then we'll just go to checkout here. And hopefully this will let me log in. So this is an unrelated bug that it clears my cart after I log in. we'll fix that in the next release. But one that I wanted to look at here is my subtotals and shippings and taxes and totals. These don't look quite right to me. So we're buying 3 of a thing that costs $8.50. So I would expect that to cost us about $25.50. But our subtotal is really weirdly and confusingly $11.50. The shipping for each one of these things is $1. But again, our shipping is coming up as a really weird number. So 15 cents worth of shipping. That's not even as much as it costs to ship one of these things, let alone 3 of them. And then it looks like there's some tax on top of this. So this tax might be right. I don't know what our tax rate is. Maybe it's 5%. So that could be right. I don't know. We'd really have to investigate it. And then there's a total down here. And this total feels like it might be right, but everything in here is just so weird. I don't even know where to start debugging this. So fortunately, what I can do is I can take a look at the Ozcode production debugger here. So if you have seen this tool before, you might be familiar with this screen. And what this tool can do is actually go in and intercept exceptions inside of your application and show you the state of your application at the time that the exception occurred. So this is a really fantastic tool, but it's not really going to help us right now because like nothing here is throwing an exception. So we don't have anything showing up in the production debugger here for us to catch onto and take a look and see what's happening. I'm not sure how we're going to get around that, except that there is a relatively new feature that's been added here called tracepoint sessions. So this does a really fabulous thing. So what it allows us to do is insert requests into our compiled application using these non-breaking breakpoints. So the application continues on and is still very performant behind the scenes, but it allows us to see the state of local variables as the application is running. So I'm going to click here on create, and I'm going to create a new tracepoint session here. So I'm going to call this one weird totals. And this here is going to give us a fairly blank screen, but what I can do is I can go up to here and I can start searching through my code to find where I think the problem is and add some instrumentation to it. So what this tool is actually doing is it is going out and it is reflecting over the code that you have deployed to production. So this particular site is deployed to Azure in just an app service. There's support for Azure, for AWS, for Docker containers, for WPF apps, basically you name it. This Ozcode production debugger can be inserted in there. But this is going out and it's actually looking at the code that I have deployed to production, and it's going to allow me to insert these breakpoints in it. So this page here is basket checkout. And I just happen to know that this page here is generated from a thing called the basket view model, I think. So I can just go here, basket view model. Okay, so I'm going to hit this. And this is going to go out and find the code for me here. So this is actually the code that is behind the basket view model. So if I flipped over to Visual Studio and I found the same thing, you can see that the code is basically exactly the same. So I'm going to take a look at my total line here and try and figure out what's going on here. So I'm going to add a little trace point here. And what I can do is I can put in any message I like here. So I'm going to say total calculation is, and then I can put in the variables that I'm interested in seeing. So I'm interested in the subtotal, and the tax, the shipping. All right, so that has added this trace point here. And I'm interested in some of these other things too, but right now I'm really interested in this total to make sure that this total is correct. So I'm going to hit start collecting here. So this is going out and it is instrumenting the code that we have in production. So once I go back over to this site here and I hit refresh on this page, everything is still broken, of course. But then when I come back over here into Ozcode, you can see that it's captured this trace point hit down here. So if I click on this, then I can see the values that were present at that time. So let's take a look and make sure that everything seems like a reasonable number here. So we're iterating over this basket view model. So we need to take a look and see kind of what's in this items collection here. So my items collection's here. Let's see if I can zoom in a little bit here. So we have this product in there. The unit price is $8.50. There's 3 of them, and then the shipping price is 1. So that all looks pretty reasonable. So we've calculated out a bunch of different things here. So we've calculated shipping at $3. Well, that seems about right because we've got 3 items at $1 shipping. Perfect. We've calculated the tax out here at $1.27.5. So that sounds like it could be right. Tax is 5%. If I pull out my trusty HP calculator here, I do that, math. Yep, that checks out. So that's right. And then the subtotal is $25.50. So that's just a unit price times quantity. So that checks out. So I think my subtotal is fine, which is kind of what we suspected anyway. So maybe there's something else that we can do in here too and take another look at this. I'm going to pause my debugging session here, and I'm going to add a little bit more logging. So I'm going to go and grab the tax here. I'm just going to add these, I think, without any comment on them. I'm going to restart this capturing and refresh the page. So this is going to go back out and do another trace point. So we've got a bunch of trace points being hit here. So I can kind of jump into this and take a look and see what's going on here. So what's going on here? This shipping price doesn't look right here. Okay, so I think I can see what's going on here is that I've taken the shipping price, I multiplied it by the quantity, then I multiplied it by just the tax rate here. And the tax rate is only 0.05. I probably want to multiply this by 1 plus the tax rate, because otherwise I'm just getting the tax rate on the shipping. I'm not getting like the total shipping cost. So that explains why my shipping numbers are so off. I mean, this should be $3.15. That makes a little bit more sense to me. And then we can take a look at some other bits in here. So I can take a look at the taxation calculation here. And I can take a look again at all the variables that are available to me here. And this one looks to me like it might be a little bit of order of operations problem here. So I think these multiplications over here get executed before my additions. So I end up with just completely the wrong numbers. So now this gives me the opportunity to go back to my actual code base, make the changes, and deploy them out into production quickly. But sometimes I want to have a little bit more information come back to me. So it might be that I'm looking to kind of gather information for a little while for this problem. So if I click on this little cog up here, by default, these trace points remain active for about 24 hours and have a limit of 1,000 hits. So we can see that we've already hit 9 of our 1,000 hits. If we kept refreshing this page, we'd eventually hit the limit and this breakpoint collection or the trace point collection would stop. But I would really like to get this information into a place where we can do some analysis on it later. And we're making use of application insights on this application too. So what we can do is actually inject that information here into our trace stream. So I have a live metrics up here, and hopefully this will work today. This has been a little bit finicky, but I can see actually here that those trace points that I put in there actually show up inside of application insights. And this is done just through a little bit of middleware that we have that intercepts the trace points inside of the Ozcode production debugger and pushes them up into application insights. So this could push it up into any third-party logging service. But for now, we're just surfacing it in here. So this information, we can now aggregate and take a look at across hundreds of requests or thousands of requests, and we can try and find trends, or we can try and find just those specific cases where a problem has occurred. And then that lets us narrow down the problem in scope and find it much more easily. And of course, all this information also ends up in this log search over here. This tends to be a little bit behind time, so we'll see if it shows up. Yep, so we can see here that this calculation was run here. And if we wanted to, we could dig in and get a bunch more information on it, or we could put a bunch more information on it with our trace point inside of Ozcode. So there's a lot of advantages to taking on this approach. First of all, the super low overhead. So the instrumentation that is added here adds almost nothing to request time. So it's still very performant, really nice to put in. And of course, once you've collected all the trace point information you want, the code is de-instrumented and runs at native speed again. We didn't need to recompile anything, so you saw us add a bunch of different trace points inside of the application there, and we didn't recompile anything. We didn't need to redeploy anything. We didn't need to struggle to reproduce this in some sort of other environment to try and get the same problems to show up in our UAT environment or in a dev environment. So there's lots of advantages to this approach, and it's one that I'm really excited about. I think this is going to be a big thing going forward. Having this facility available to you allows you to really trace problems and track problems down much more quickly than you would normally be able to. So I think that was kind of pretty much everything that we wanted to talk about today. But we have a Slack channel, I think, available for anybody who has any questions. And of course, if you have questions now, you can probably just ask them and we'll see if we can get those answered.
Awesome. Thanks so much, Simon. So I'll go ahead and chime in on some of the questions that have been asked in the Slack channel and answer those as we go through. So one of the questions were about how does Ozcode obtain your source code, Simon? You were showing that you were navigating through code, doing the equivalent of a control T in ReSharper or Visual Studio, and suddenly you had available to you the code that's running inside of your production environment on Azure. So how did that happen?
Oh, black magic.
Good answer.
We have an agreement with dark lords of various types, but no, actually, I mean, any code that gets compiled in .NET can be decompiled if you're not running it through some sort of an obfuscation tool. So it is possible for Ozcode to kind of reflect over that code and extrapolate what the code was that went into that. There's sometimes some minor differences you might see, like oftentimes the compilers will optimize out temporary variables and those sorts of things. So if we went back and looked really closely here, you can see that I've put these kind of temporary variables here. And if you were to look at the actual code that ends up in the Ozcode debugger, those variables have been optimized out by the compiler. So there are some minor differences, but yeah, this does allow you to decompile the code. And there's lots of tools out there like .NET Reflector and things like that can decompile code and give you back a reasonable proximity to what it was that you wrote in the first place.
Awesome. And then another question was about, does that work for different types of programming languages? I'll chime in and say that as you said, any .NET code can be decompiled unless it's been obfuscated. So even if we have, for example, VB.NET code that's running in production, you'll be able to use the Ozcode production debugger on it just fine. The only sort of slight weird thing is that it will be decompiled as C# code, not as VB.NET code. Now, the other sort of question was, you know, what are the advantages of the decompilation approach? One other advantage, and in comparing it to other tools, is that even if we're using third-party NuGet library that we don't have the PDBs or the source code for, we'll actually still be able to debug it. So if we have one of those cases where the issue is actually inside of a third-party library, this does not give us any issues. Alrighty. Another question from Andrew: is it using ETW under the covers? So the production debugger uses a multitude of techniques. It uses ETW. It uses bytecode instrumentation. It uses pretty much the same sort of technology that is used by an APM such as Datadog, New Relic, Dynatrace. So if you have one of those agents installed, the Ozcode, the technology that's powering the Ozcode production debugger is pretty much the same thing. Only we're using that technology to give you production debugging insights rather than performance metrics. So I think that covers all of the questions, but I do encourage everyone who has not yet joined the Slack channel, please go ahead and do join us. It's a great way for you to keep in touch with the Ozcode team and get your answers and feedback to us and get quick responses. We're very, very responsive when we talk to our customers, so love to keep the conversation going. Simon, is there a coupon slide that we should be showing, perhaps?
Ooh,
not sure.
Maybe. I don't know that I have that.
Okay, so there will be a coupon for anyone that's attended this webinar. You will be receiving it as an email following for the webinar. So be sure to check out your email box and make sure you take advantage of that. So with that, I see that we have no more. What are the production debugger developments for the near future? So there's a question here for what is our roadmap? So a few things that I can already list out are things like conditional trace points, being able to say, hey, I only want to hit this trace point if a certain condition on the code is available. And then on top of that, you can layer the integrations, such as we've shown an application insights integration, but you could also do something like a Slack integration where you say, if this trace point hits with this condition, I want to be notified immediately to Slack. So that's one tiny sort of preview, but there are lots of other features coming in that are very much in depth that I can't go into right now, but we will be sharing a roadmap information through our website and our newsletter. So feel free to follow us and we'll get you more and more information as the year progresses. Alrighty, so I think we're out of questions. So I'll use this opportunity to say thank you very much to Simon again for this lovely webinar, and thank you to our lovely audience for being here. And we'll see you on the next webinar.
Thank you.
Bye-bye.